From the dawn of time, humanity has gazed upon the stars with wonder and trepidation. The vast expanse of the cosmos holds countless mysteries, but few are as captivating as black holes. Often portrayed in science fiction as gateways to other dimensions or cosmic vacuum cleaners, black holes are indeed among the most bizarre and fascinating objects in the universe. These celestial objects are so dense that their gravitational pull traps even light itself, rendering them invisible to our eyes. Their existence was predicted by Einstein's theory of general relativity, which describes gravity as the curvature of space-time caused by massive objects. Despite their invisibility, astrophysicists can detect and study black holes by observing their effects on nearby stars and gas clouds. The study of black holes pushes the boundaries of our understanding of the universe, challenging our preconceived notions of space, time, and gravity. Black holes are not merely cosmic oddities. They are fundamental to the evolution of galaxies, including our own Milky Way. Their immense gravity can influence the formation of stars and the dynamics of entire galaxies. Supermassive black holes, millions to billions of times the mass of our Sun, are thought to reside at the centers of most galaxies, shaping their destinies. These enigmatic objects continue to intrigue scientists and the public alike. The quest to unravel their secrets has led to groundbreaking discoveries and fueled our imagination. From the first ever image of a black hole's shadow captured by the Event Horizon Telescope to the detection of gravitational waves from black hole mergers, our understanding of these celestial objects is constantly evolving. Join us as we journey into the heart of black holes, exploring their formation, characteristics, and the profound impact they have on our universe. What exactly is a black hole? Imagine the Earth squeezed into the size of a marble. That's the kind of density we're talking about. It's a region of space-time where gravity is so strong that nothing, not even light, can escape its pull. This extreme density arises from the death of a massive star. When a star much larger than our Sun runs out of fuel, it collapses under its own gravity. This collapse compresses the star's core to an incredibly small and dense point called a singularity. Surrounding the singularity is an invisible boundary called the event horizon. The event horizon is the point of no return. Anything that crosses this boundary, whether it's a spaceship, a planet, or even light itself, is forever trapped inside. Think of it like a one-way membrane in space-time. Imagine you could shine a flashlight towards a black hole. As the light from your flashlight gets closer to the event horizon, it starts to bend more and more due to the intense gravity. Eventually, the light gets bent so much that it can't escape, falling into the black hole like a ball rolling down a hill. What's fascinating is that for an observer watching from a safe distance, anything that falls into a black hole appears to freeze in time at the event horizon. This is because the black hole's gravity warps time itself, making time flow slower the closer you get to it. It's important to remember that black holes are not cosmic vacuum cleaners. They don't suck up everything around them. If our Sun were to suddenly become a black hole, don't worry, it won't. Earth would continue to orbit it just as it does now, albeit in darkness. So, what lies at the heart of a black hole? Within the singularity. Here, our current understanding of physics breaks down. The singularity is thought to be a point of infinite density and zero volume, a concept that is difficult to grasp. To understand what happens inside a black hole, we would need a theory that combines Einstein's general relativity, which governs the very large, with quantum mechanics, which governs the very small. This is one of the biggest challenges in modern physics. Despite these challenges, black holes offer a unique laboratory for testing the limits of our knowledge. They are windows into the most extreme environments in the universe, where gravity reigns supreme. By studying them, we can hope to unlock some of the universe's deepest secrets. To understand how black holes form, we need to journey back to the birthplaces of stars. Stars are born in massive clouds of gas and dust scattered throughout galaxies. These clouds, called nebulae, are cosmic nurseries for star formation. Gravity plays a crucial role in this process. Regions of higher density attract surrounding matter. As material clumps together, the gravitational pull intensifies. The core heats up under immense pressure, igniting nuclear fusion. Our Sun, a typical star, has been in this state of equilibrium for billions of years, steadily fusing hydrogen into helium in its core. This balance, however, cannot last forever. Eventually, a star will exhaust the hydrogen fuel in its core. When this happens, the outward pressure from nuclear fusion weakens, and gravity begins to take over. For stars like our Sun, this leads to a relatively peaceful death. They expand into red giants, shedding their outer layers into space. The core, however, continues to collapse, eventually forming a dense, hot object called a white dwarf. White dwarfs are essentially stellar embers, slowly cooling over billions of years. But for stars much more massive than our Sun, the story takes a dramatically different turn. These stellar giants have much stronger gravitational forces at play, and their end is anything but peaceful. When a massive star runs out of hydrogen fuel, it starts fusing heavier elements in its core, like helium, carbon, and oxygen. This process releases even more energy, temporarily delaying the star's demise. However, this reprieve is short-lived. As the star fuses heavier and heavier elements, its core becomes increasingly dense and hot. Iron, the final element produced in this stellar furnace, cannot be fused further. At this point, the outward pressure from nuclear fusion ceases altogether, and gravity wins the battle. The core of the star, now made mostly of iron, collapses in on itself at an astonishing speed, approaching a quarter of the speed of light. This implosion triggers a shockwave that reverberates through the star's outer layers, blasting them off into space in a spectacular explosion known as a supernova. Supernovae are among the most luminous events in the universe, briefly outshining entire galaxies. They scatter the elements forged in the star's core far and wide, seeding interstellar space with the building blocks of planets and even life itself. Meanwhile, the core of the star continues its relentless collapse. If the core is massive enough, gravity overwhelms all other forces, squeezing it down to an infinitely small point, a singularity. The event horizon forms around this singularity, marking the point of no return. A black hole is born. The birth of a black hole from the death throes of a massive star is a testament to the immense power of gravity. These cosmic monsters, once shrouded in mystery, are now recognized as fundamental players in the grand cosmic drama. Imagine a giant rubber sheet stretched taut. If you place a bowling ball in the center, it will create a dip in the sheet. This is a simple way to visualize how gravity works, according to Einstein's theory of general relativity. Massive objects like stars and planets warp the fabric of space-time around them. Now, imagine replacing the bowling ball with something much denser, something like a black hole. The dip in the rubber sheet becomes an infinitely deep well, a bottomless pit in the fabric of space-time. This is the essence of a black hole's gravitational pull, an irresistible force that warps the very fabric of the universe. The event horizon, the point of no return, marks the boundary of this gravitational abyss. Anything that crosses the event horizon, whether it's a beam of light or a giant star, is irreversibly drawn towards the singularity at the black hole's center. The singularity is perhaps the most mind-boggling aspect of a black hole. It's a point where all the matter that ever fell into the black hole is compressed into an infinitely small space. Imagine squeezing all the information contained in a library into a single point. That's the kind of density we're talking about. At the singularity, our current laws of physics break down. We need a new theory, one that unifies gravity with quantum mechanics, to truly understand what happens at this point of infinite density. Some physicists speculate that the singularity might be a gateway to other universes or dimensions, but these ideas remain highly speculative. Despite the mysteries surrounding the singularity, we can still study the effects of its immense gravity on the surrounding space and time. One of the most striking phenomena is the warping of time near a black hole. As matter falls towards a black hole, it rarely falls straight in. Instead, it spirals inwards, forming a swirling disk of gas and dust known as an accretion disk. Think of water swirling down a drain, but on a much grander scale. These accretion disks can be incredibly hot, reaching millions of degrees Celsius. This intense heat is generated by friction as the particles in the disk rub against each other at incredibly high speeds. This heat causes the accretion disk to radiate brightly, emitting light across the electromagnetic spectrum, from radio waves to X-rays. In some cases, the intense magnetic fields around a black hole can channel jets of superheated plasma away from the accretion disk. These jets can extend for thousands of light years, blasting out into the surrounding galaxy at nearly the speed of light. While we can't see black holes directly, we can detect their presence through their interactions with surrounding matter. The intense gravity of a black hole can distort the light from objects behind it, creating a phenomenon known as gravitational lensing. Another way we can see black holes is through the detection of gravitational waves. These ripples in space-time are produced by the acceleration of massive objects, such as the collision of two black holes. In 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, made history by detecting gravitational waves from the merger of two black holes, a discovery that sent shock waves through the scientific community. These discoveries, along with ongoing observations of black holes and their surroundings, are helping us piece together the story of these enigmatic objects and their role in the evolution of the universe. The journey into the heart of black holes is far from over. In fact, it's just beginning. Far from being mere cosmic oddities, black holes play a pivotal role in the grand scheme of the universe. Their influence extends far beyond their event horizons, shaping galaxies and the cosmos. As galaxies evolved, so did the supermassive black holes at their centers. The energy released by these active galactic nuclei influenced star formation rates. It's a cosmic dance of gravity, matter, and energy, shaping the universe today. The Milky Way, our home galaxy, is no exception. At the heart of our galaxy lies Sagittarius A, a supermassive black hole with a mass about 4 million times that of our Sun. While it may seem counterintuitive, this monstrous object at the heart of our galaxy actually plays a crucial role in its stability. The immense gravity of Sagittarius A holds the Milky Way together, preventing it from flying apart as it rotates. Think of it like the Sun's gravity holding the planets in orbit. but on a much grander scale. The black hole's gravitational pull keeps the stars in the galaxy on their paths, ensuring the Milky Way's spiral structure remains intact. The influence of supermassive black holes extends beyond their host galaxies. They can influence the motion of entire galaxy clusters, the largest known structures in the universe held together by gravity. Black holes, in a sense, act as the invisible guardians of the cosmic balance, shaping the large-scale structure of the universe. Black holes are not just fascinating objects of study for astronomers, they are also cosmic laboratories for physicists. They represent the most extreme environments in the universe, where gravity is at its strongest and our current understanding of physics is pushed to its limits. Einstein's theory of general relativity, which describes gravity as the curvature of space-time, has been incredibly successful in explaining the behavior of black holes on large scales. However, at the singularity, where gravity becomes infinitely strong, general relativity breaks down. We need a new theory, one that unifies gravity with quantum mechanics, to fully understand what happens at this point. Black holes provide a unique opportunity to test these theories. By studying the behavior of matter and light near the event horizon, we can glean insights into the nature of gravity and the fundamental laws of physics. The study of black holes could lead to breakthroughs in our understanding of the universe and its origins. The quest to understand black holes is ultimately a quest to understand the quantum nature of gravity. Quantum mechanics governs the very small, and general relativity governs the very large. They seem incompatible at the most fundamental level. Black holes provide a unique testing ground for unifying these theories. Theories like string theory propose space-time is quantized. Black holes could unlock a deeper understanding of the quantum universe. As we conclude our journey into the heart of black holes, we are left with a sense of awe and wonder at the sheer scale and mystery of the universe. These cosmic behemoths have emerged as fundamental players in the grand cosmic drama. They are the ultimate endpoints of stellar evolution, creating objects so dense that not even light can escape. Black holes are integral to the fabric of the universe. Their influence shapes galaxies, matter distribution, and even time itself. The study of black holes reveals the interconnectedness of space, time, and gravity. Discoveries like the first image of a black hole's shadow and gravitational waves deepen our fascination. They remind us of the vastness of the unknown and the universe's capacity to amaze. Black holes, despite their invisibility, have emerged as the unseen architects of the cosmos. Their immense gravitational pull acts as a cosmic sculptor, shaping the galaxies we observe today. Supermassive black holes, lurking at the centers of most galaxies, serve as gravitational anchors, holding these vast collections of stars together and influencing their evolution over billions of years. The relationship between black holes and their host galaxies is a delicate balance of power and influence. Black holes can fuel the growth of galaxies by accreting surrounding gas and stars, releasing tremendous amounts of energy in the process. This energy can trigger star formation, shaping the galaxy's overall structure and evolution. However, black holes can also stifle star formation by releasing powerful jets of energy that heat up surrounding gas, preventing it from collapsing to form new stars. This delicate interplay between black holes and their surroundings highlights the interconnectedness of the cosmos, demonstrating how even the most extreme objects can play a crucial role in shaping the universe we observe. One of the most profound implications of black holes is their ability to distort space-time. Einstein's theory of general relativity explains the behavior of black holes. Near a black hole, time slows down, space warps, and physics are pushed to their limits. The event horizon marks the boundary of a black hole's gravitational dominion. Anything crossing this boundary is drawn towards the singularity. At the singularity, our understanding of physics breaks down. Studying black holes offers insights into gravity and space-time. As we look towards the future of black hole research, we are filled with anticipation and excitement. New telescopes and observatories are poised to revolutionize our understanding of these enigmatic objects. The Event Horizon Telescope, which captured the first ever image of a black hole's shadow, is being upgraded for sharper images. Gravitational wave astronomy is rapidly advancing, allowing us to hear black hole collisions. New detectors promise to detect more distant black hole mergers, providing insights into their evolution. The journey into black holes will continue to captivate and inspire scientific inquiry for generations.